Hello and welcome back. We're going to be continuing our discussion on section 5.3, inverse trig functions. Now we left off here on this slide. Hopefully you did get a chance to practice C, D, E, and F on your own. I'm going to go ahead and very quickly just share the answers for those four with you. For C, we want to find the angle that gives us the sine ratio of negative square root 3 over 2. I'm going to go ahead and bring up a unit circle for us to refer to. So looking for the angle that gives us a sine value of negative square root 3 over 2, I see that that sine value occurs in the third quadrant. I have an angle of 4 pi over 3, and it also occurs in the fourth quadrant. I have an angle of 5 pi over 3. Now remember that sine is only defined from negative pi over 2 to pi over 2, so I'm going to use the angle 5 pi over 3 because that is in the interval that I'm looking for. So sine of, and then the angle is 5 pi over 3, which does give us a sine value of negative square root of 3 over 2. For D, I'm looking at an angle of 2 pi over 3, so I want the ratio. Here I want the sine value. I have the angle, so I go around to the angle of 2 pi over 3, and I see that that sine value is square root 3 over 2. So I have an inverse sine of square root 3 over 2. And again, inverse sine is only defined from negative pi over 2 to pi over 2. So that's the first and the fourth quadrant. So I need to look for an angle with a value of square root 3 over 2 in the first and the fourth quadrant. And that angle occurs at pi over 3, where that sine value is square root 3 over 2. So I am looking for the angle pi over 3. Cosine of negative pi over 3 now. If I go to negative pi over 3, that's going to be here at 5 pi over 3, which is equivalent to negative pi over 3. So the cosine value at that angle is going to be 1/2. And I am asked to find the angle that gives me a cosine value of 1/2. Now, if I'm talking inverse cosine, I need to be looking at the interval from 0 to pi, so that's only this top half of the unit circle. So from 0 to pi, I'm looking for a cosine value of positive 1/2, and I see that here at pi thirds. So the angle I'm looking for is pi thirds. For my tangent function, I want a tangent. Again, inverse tangent is only defined in the first and the fourth quadrant, so I'm looking for a positive tangent value of square root 3. Tangent is going to have a positive value here in the first quadrant where both sine and cosine are positive. So when I take the ratio of two positive numbers, I'll get a positive tangent. Tangent will have a ratio of positive square root 3 at the angle pi over 3. So the angle that gives me that tangent measure is pi over 3, and now I am asked to find the tangent of that angle. So we are looking for a tangent at pi thirds, and pi thirds is in that first quadrant. Tangent is square root 3 over 2 over 1/2. And just like we've done in the past, I can take that denominator and instead multiply by its reciprocal. Reducing my fractions, I will get square root of 3. Moving on, I'd like for you to take a moment to pause the video and practice these next couple on your own. Now we are going to be using two different trig functions instead of the inverse of a trig function and itself. So using my unit circle, I'm going to evaluate the sine of 11 pi over 6. 11 pi over 6 is in the fourth quadrant, and I see a sine value of negative 1/2. So I want the inverse cosine of negative 1/2, or I want the angle that gives me a cosine value of negative 1/2. Inverse cosine is defined only in the first and the second quadrant. So I'm going to look in the first and the second quadrants for a cosine or an x value of negative 1/2, and I see that occur at 2 pi over 3. So this simplifies down to 2 pi over 3. In example 536, I'm looking for a sine value of square root 2 over 2, and I want the angle that gives me that sine value. Inverse sine is defined in the first and the fourth quadrant, so I'm looking only in these two quadrants for a positive square root 2 over 2, and I see that occurring at pi fourths. So now I am looking for the cosine of pi fourths. So I go to pi fourths, find the x value or the cosine value at that coordinate, and I see that it is also square root 2 over 2. Now next in our notes, we've got a couple questions that look very similar, but they're slightly different. So I'm going to ask you again to take a moment to pause the video and try going through these two on your own before I guide you through them. What you might notice is that this 13 pi over 6 is not an angle on our unit circle. If we simplify it down, we will see that this is actually greater than 2 pi. So my first step here is to simplify that angle by subtracting a multiple of 2 pi from it. So if I go around my circle to 13 pi over 6, that's going to complete a rotation and then continue on. So I'm going to subtract 2 pi from that 13 pi over 6. To have a common denominator, I multiply the numerator and the denominator by 6, giving me 13 pi over 6 minus 12 pi over 6, which leaves me with just pi over 6. So I'm actually looking for the cosine of pi over 6. We just rotated fully around the circle once before we ended at our angle. Either way, that cosine value is going to be square root of 3 over 2. And now I want the angle that gives me a sine value of square root 3 over 2. And we are looking in either the first or the fourth quadrant since we are dealing with an inverse sine. So in the first quadrant, I have a positive sine value of square root 3 over 2 at the angle pi over 3. So inverse sine of square root 3 over 2 is pi over 3. Example 536 is going to be a little bit similar, but you might notice that I have no ratios of 4 over 5 anywhere on my unit circle. So I'm actually going to use a slightly different approach. I am first looking for the inverse cosine of 4/5, which means I want an angle that gives me a ratio of 4/5 for my cosine. Instead of using the unit circle, I can use triangles to help me figure out what my angle might be. So I'm going to go ahead and draw out my triangle. Generally, we use our unit circle because our ratios are already set up for us and it's a little bit more direct. But if I don't have a value that's on the unit circle, I can go ahead and refer back to triangles. Theta will just be one of my angles in my triangle, and then of course I will have a right angle since we are dealing with a trig function. If we remember back to SOHCAHTOA, your cosine function is the relationship of the adjacent and hypotenuse of your right triangle. So I am looking here at the adjacent side, the side that's touching my angle theta, and the hypotenuse, which is always across from that 90-degree angle. Here, my adjacent side is 4 and my hypotenuse will be 5 because the ratio that I'm given is 4 over 5. So my A is 4 and my hypotenuse is 5. Now what we are really asked for is the sine of the angle that gave us a cosine value of 4/5. So in this triangle, whatever this angle is, it's unknown, it will give us a cosine value of 4/5. So now what I want actually is the sine of that theta. So I don't actually care what the theta is. This relationship set up my triangle for me. It allowed me to put theta in the correct place. Now that I have theta in the correct place, with my 4 and my 5 sides labeled, I can now find the sine of whatever that angle is without actually knowing what that angle is. I will just complete this triangle using the Pythagorean theorem. So I'll complete this triangle by calling this missing side y, since it is going to help us find our sine function. And using the Pythagorean theorem, I've got 4 squared plus y squared, those are my two legs, is equal to my hypotenuse, which is 5 squared. So 16 plus y squared is equal to 25. Subtracting 16 from both sides, I find that y squared is 9. So y is either the positive or negative square root of 9, which is 3. So now we need to decide, is it going to be a positive 3 or a negative 3? So here are our options. I've got a positive 3 over 5 or a negative 3 over 5. And I got that because sine is the opposite side, which is the y that we just found, over my hypotenuse, which is always 5. So we need to choose between these two. Well, if we go back to our original angle, our angle came from inverse cosine of 4/5. Well, remember that inverse cosine is only defined from 0 to pi, which means that our angle was somewhere above the x-axis. There are no negative sine values for any angle here. So it doesn't really matter what angle we were using, what theta we were using. We know, since it came from an inverse cosine, that it must be a positive sine value. If you go through and look at all of these sine values, none of them are negative. Therefore, the sine that I am looking for is going to come from a theta that gives us a positive sine value. So my ratio here for sine is positive 3/5. We're going to do a couple more using triangles to help us evaluate the values of these trig functions. So here I want the tangent of inverse sine of x minus 1. So I'll go ahead and start off with the fact that my angle is somewhere between negative pi over 2 and positive pi over 2. So this inverse sine is an angle, a theta, that's somewhere in this interval. So I'm going to set up a reference triangle. Since I can't use that x minus 1 straight from my unit circle, and I'll put theta down in this bottom left angle. And I am going to use my SOHCAHTOA rule to help me complete the triangle. Sine is my opposite side over my hypotenuse based on my SOHCAHTOA rule. So what this inverse sine is telling us is that there is an angle somewhere, a theta, that gives us a sine value of x minus 1, or in other words, sine of some angle. Again, that angle must be from negative pi over 2 to pi over 2. Sine of that angle equals x minus 1. So that ratio sine is equal to opposite over hypotenuse, so I will write this as a fraction, over 1. And now I can fill in 2 of the sides on my triangle. Looking at my theta, the opposite side will be x minus 1. And then my denominator is 1, which means my hypotenuse is 1. So the numerator is the opposite side of theta, denominator is the hypotenuse. Well, tangent is opposite over adjacent. So from theta, I need the opposite side, which I have, but I need the adjacent side as well, which I don't have. But again, I can use Pythagorean's theorem to find this. So I take my 2 legs and square them, adding them together, and that equals my hypotenuse squared. So I've got x minus 1 times x minus 1 plus a squared is equal to 1 squared is 1. Multiplying this out, I've got x squared minus 2x plus 1 plus a squared is equal to 1. And I'm trying to solve for a, so I'm going to go ahead and move everything over to the right-hand side by subtracting x squared, adding 2x, and subtracting 1 from both sides. So I subtract x squared, add 2x, and I should subtract 1. So I've got a squared equals 1 minus x squared plus 2x minus 1. I've got a positive 1 and a negative 1 that are going to be inverses. So a squared is equal to negative x squared plus 2x. Square rooting both sides then, I've got a is equal to the square root of negative x squared plus 2x. This is my adjacent side, so I can then find tangent by taking the ratio of the opposite to the adjacent. So the tangent of that angle theta would be x minus 1 is my opposite side, over my adjacent side, which is the square root of negative x squared plus 2x. There is one more example in your notes that would be good to practice, and then I do have an exit ticket for you today. Thanks so much for watching. Have a great rest of your day.